Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Apollodorus of Damascus, a name resonating through the annals of Roman architectural and engineering prowess, stands as a monumental figure of innovation and design. His story, inextricably linked to the zenith of the Roman Empire under Emperor Trajan, offers a compelling study of how technical ingenuity, artistic vision, and imperial ambition converged to shape the built environment of antiquity. Born in Damascus, a city renowned for its rich cultural heritage and strategic importance within the Roman East, Apollodorus received an education steeped in both Hellenistic and Roman traditions. This background provided him with a unique perspective, blending the aesthetic sensibilities of the Greek world with the practical engineering acumen of Rome. His early training likely encompassed a comprehensive curriculum of mathematics, geometry, and mechanics, equipping him with a theoretical foundation necessary for his later architectural endeavors. Furthermore, exposure to the established building practices of the Eastern Roman provinces have instilled in him a deep appreciation for the challenges and opportunities inherent in large-scale construction projects. The ascent of Trajan to the imperial throne in 98 AD marked a turning point for Apollodorus. Trajan, a military leader and administrator with a keen interest in public works, recognized Apollodorus's exceptional talents and appointed him as his chief architect. This appointment placed Apollodorus at the helm of an ambitious program of urban renewal and infrastructure development designed to enhance the glory of Rome and consolidate imperial power. The projects undertaken during Trajan's reign, particularly those within the city of Rome itself, represent a remarkable synthesis of architectural innovation and engineering skill, all bearing the unmistakable imprint of Apollodorus's design philosophy. Central to Apollodorus's legacy is his design and construction of Trajan's Forum, a sprawling complex intended to serve as the new heart of Rome. The existing Roman Forum, a venerable space steeped in history and tradition, had become increasingly congested and inadequate to accommodate the burgeoning needs of the imperial capital. Trajan envisioned a grander, more functional space that would not only facilitate commerce and administration, but also serve as a lasting monument to his military achievements and civic virtues. The construction of Trajan's Forum presented formidable challenges. The site, located in a densely populated area between the Capitoline and Quirinal hills, required extensive excavation and the removal of significant amounts of earth and rock. Apollodorus ingeniously addressed this problem by terracing the site and employing innovative construction techniques to stabilize the surrounding slopes. The Basilica Ulpia, a massive structure dominating the northern side of the Forum, exemplifies Apollodorus's mastery of spatial design and structural engineering. This grand hall, intended for use as a low-cost commercial center and public gathering space, featured a vast central nave flanked by double colonnades and apses at either end. The sheer scale of the Basilica Ulpia demanded innovative structural solutions. Apollodorus employed a sophisticated system of barrel vaults and concrete construction to create a light-filled interior space, free from the encumbrances of internal supports. This innovative use of concrete, a material perfected by Roman engineers, allowed for the creation of large, open spaces that would have been unthinkable using traditional building methods. The Basilica Ulpia served as a model for later Roman basilicas and Christian churches, demonstrating the enduring influence of Apollodorus's architectural vision. Adjacent to Trajan's Forum, Apollodorus designed and oversaw the construction of Trajan's Market, a multi-level complex of shops, offices, and warehouses. This structure, built into the side of the Quirinal Hill, represents a remarkable feat of urban planning and engineering. Trajan's Market was designed to address the growing need for commercial space within the city of Rome, providing a centralized location for the sale of goods and services. The complex was organized around a network of interconnected streets and stairways, allowing for easy access to the various levels. Apollodorus employed a variety of construction techniques, including the use of brick-based concrete and barrel vaults, to create a durable and functional structure. The innovative design of Trajan's Market, with its efficient use of space and its integration into the surrounding urban fabric, stands as a testament to Apollodorus's ingenuity as an architect and urban planner. It showcased a solution to the problems of commerce, public space, and commemoration within a dense metropolis. Apollodorus's designs were influenced by earlier Roman architects and engineers, most notably Vitruvius, whose treatise De Architectura served as a foundational text for Roman building practices. Vitruvius emphasized the importance of structural integrity, functionality, and aesthetic harmony in architectural design, principles that are clearly evident in Apollodorus's work. However, Apollodorus went beyond simply replicating Vitruvian principles. He expanded upon them, pushing the boundaries of what was structurally and aesthetically possible. He adopted and refined the Roman use of concrete, allowing for larger and more complex structures than previously achievable. He also demonstrated a keen understanding of spatial relationships, creating buildings that were both functional and visually impressive. In addition to his architectural achievements, Apollodorus was also a skilled engineer with a deep understanding of military technology. He authored treatises on siege engines and other military devices, demonstrating his expertise in mechanics and ballistics. These theoretical works, while less well known, and his architectural designs provide further evidence of his intellectual breadth and his commitment to advancing the state of engineering knowledge. They likely drew upon existing knowledge of Hellenistic siege technology, adapting and improving upon these designs for Roman military applications. His writings would have provided detailed instructions on the construction and operation of various siege engines, including catapults, ballistae, and siege towers, along with calculations of projectile trajectories and impact forces. This theoretical work on siege engines complemented his practical experience in designing and constructing fortifications and other military structures. Apollodorus of Damascus, beyond his contributions to civic architecture and engineering theory, left an indelible mark with his design and execution of the Column of Trajan. This monumental structure stands as a testament to Roman engineering prowess, architectural innovation, and imperial propaganda, all skillfully interwoven. Its construction presented immense technical challenges, from the initial quarrying of marble to the intricate carving of its spiraling narrative. The column's creation began in the marble quarries of Carrara, where massive blocks were extracted. These blocks, destined to become the individual drums of the column, demanded precise cutting and shaping. Specialized tools and techniques were employed to ensure uniformity and structural integrity. The transportation of these enormous marble drums, each weighing several tons, from the quarries to Rome posed a significant logistical hurdle. Roman engineers likely utilized a combination of land and water routes, employing specially designed carts and barges to navigate the terrain and waterways. Upon arrival in Rome, the drums were hoisted into place using a complex system of cranes and pulleys, a testament to the sophistication of Roman lifting technology. The column's internal structure features a spiral staircase that ascends to the viewing platform at the top. Apollodorus ingeniously designed this staircase within the confines of the column, ensuring both structural stability and ease of access. The geometry of the spiral is meticulously calculated, with each step precisely positioned to maintain a consistent rise and run. The structural mechanics involved in supporting the staircase and the overlying marble cladding demanded a deep understanding of load distribution and material properties. The staircase provided access to the viewing platform atop the column, offering panoramic views of Trajan's Forum and the surrounding city. The continuous spiral frieze that adorns the exterior of the column depicts Trajan's Dacian wars in vivid detail. This intricate carving presented a unique artistic and logistical challenge. The frieze, measuring approximately 1 meter in height, wraps around the column 23 times, narrating the story of the two Dacian campaigns in a continuous sequence of scenes. The execution of this monumental artwork required a team of skilled sculptors working under Apollodorus's direction. The sculptors employed a variety of techniques to create the frieze, including carving in high relief to accentuate the figures and details. The logistical coordination required to manage the sculptors, transport materials, and ensure the accuracy of the narrative was considerable. The column functions as a visual narrative, conveying the story of Trajan's victories to the citizens of Rome and posterity. The frieze depicts a wide range of scenes, from battles and sieges to the construction of fortifications and the negotiation of treaties. The figures are rendered with remarkable detail, capturing their expressions, gestures, and clothing. The frieze subtly adapts its scale and perspective to account for the viewer's changing vantage point as they ascend or imagine ascending the column. Figures in the lower registers are larger and more detailed, while those in the upper registers are smaller and more stylized. This adjustment in scale ensures that the frieze remains legible and visually engaging from ground level. While the Column of Trajan served as a model for later commemorative monuments, including the Column of Marcus Aurelius in Rome, it was never truly replicated. The sheer scale, artistic quality, and engineering complexity of the Column of Trajan made it a unique achievement. Later columns often simplified the design, reduced the scale, or employed different materials. The Column of Trajan stands as a singular example of Roman imperial art and engineering, unmatched in its ambition and execution. The design of the Column of Trajan reflects the influence of Hellenistic relief carving traditions. Monumental sculpture, such as the pergamon altar, provided precedents for narrative friezes and dynamic compositions. The pergamon altar, with its dramatic depiction of the battle between the gods and giants, showcased the potential of relief sculpture to convey complex narratives and evoke powerful emotions. Apollodorus likely drew inspiration from these earlier examples, adapting and refining the techniques of Hellenistic sculpture for his own purposes. Specific examples of earlier monumental sculpture that may have informed his work include the friezes of the Mausoleum at Halicarnassus, which depicted scenes from Greek mythology and history. These earlier works demonstrated the use of relief sculpture to create a sense of depth, movement, and drama. The Column of Trajan exerted a significant influence on Renaissance artists and architects who studied and drew inspiration from its design. Artists such as Donatello and Michelangelo were deeply impressed by the column's artistic quality and its depiction of human anatomy. Architects such as Bernard and Raphael studied the column's structural design and its innovative use of space. The spiral staircase within the column served as a model for later spiral staircases in Italian palazzi. The Palazzo Farnese in Rome, designed by Michelangelo, features a grand spiral staircase that echoes the design of the Column of Trajan. Renaissance artists and architects also drew inspiration from the column's narrative frieze, adapting its compositional techniques and its attention to detail in their own works. The influence of the Column of Trajan can be seen in the frescoes of the Sistine Chapel, where Michelangelo employed similar techniques of perspective and foreshortening to create a sense of depth and drama. In summary, the Column of Trajan represents the culmination of Apollodorus' skills as an architect, engineer, and artist. Its construction demanded expertise in quarrying, transportation, lifting, and carving. Its design reflects a deep understanding of geometry, mechanics, and perspective. Its artistic quality is a testament to Apollodorus' mastery of Roman and Hellenistic sculptural traditions. The column stands as a lasting monument to Trajan's achievements and a powerful symbol of Roman imperial power. It provided inspiration for generations of artists and architects, solidifying Apollodorus' place as one of the most influential figures in the history of architecture. Apollodorus of Damascus possessed talents extending well beyond the realm of civic architecture. His expertise significantly impacted Roman military engineering. He authored a theoretical treatise on siege engines known as Practicality, of which fragments, alongside secondary accounts, permit a reconstruction of its key principles and innovations. The genesis of Apollodorus' work in siegecraft lay in the rich history of military engineering traditions among both the Greeks and Romans. The Greeks, particularly during the Hellenistic period, had pioneered sophisticated siege engines, such as the torsion-powered catapults. Archimedes' legendary defense of Syracuse against the Roman fleet during the Second Punic War showcased the devastating potential of these machines. Roman military engineers, including Vitruvius, author of *to Architectura*, further refined and standardized siege technology, emphasizing practicality and efficiency in deployment. Apollodorus built upon this foundation, incorporating existing knowledge while introducing novel design elements and theoretical refinements. Practicality, as it is understood through surviving fragments and historical descriptions, presented a systematic approach to siege warfare, encompassing the design, construction, and deployment of various siege engines. The treatise likely included detailed mathematical calculations for determining projectile trajectories, optimizing lever systems, and maximizing the power of torsion springs. Apollodorus emphasized the importance of adapting siege engines to the specific terrain and fortifications of the target city, advocating for a flexible and adaptable approach to siege warfare. Specific types of siege engines that Apollodorus likely designed or improved include ballistae, catapults, and siege towers. The ballista, a torsion-powered artillery piece, launch heavy bolts or stones with considerable accuracy and range. Apollodorus likely refined the design of the ballista, improving its accuracy and range through precise calculations of torsion and projectile weight. The catapult, another torsion-powered engine, launched heavier projectiles, such as large stones or incendiary devices, with devastating effect. Apollodorus may have explored new materials and construction techniques to increase the power and durability of catapults. Siege towers, mobile wooden structures that allowed attackers to scale city walls, were a common feature of Roman sieges. Apollodorus may have enhanced the design of siege towers, incorporating features such as reinforced walls, internal ramps for rapid troop deployment, and articulated bridges for connecting to the enemy's ramparts. The mathematical and mechanical principles underlying the design of these engines were central to Apollodorus' approach. He possessed a deep understanding of geometry, trigonometry, and mechanics, which he applied to optimize the performance of siege engines. The calculation of projectile trajectories involved determining the optimal launch angle and projectile weight to achieve maximum range and accuracy. This required a thorough understanding of ballistics and air resistance, as well as precise measurements of the engine's power output. The optimization of lever systems involved calculating the ideal ratio of lever arms to maximize the force applied to the projectile. This required a careful consideration of the materials used in the lever system and the forces they could withstand. The utilization of torsion springs, typically made of twisted sinew or hair, was a key element in the design of ballistae and catapults. Apollodorus likely conducted experiments to determine the optimal materials and construction techniques for torsion springs, maximizing their power output and durability. The practical applications of Apollodorus's siege engines in Roman military campaigns are documented, though direct attribution remains challenging due to the nature of historical records. Trajan's Dacian Wars, which Apollodorus accompanied as chief engineer, provided ample opportunities to test and refine his siege technology. The Dacian fortresses, with their formidable stone walls and strategic locations, presented a significant challenge to the Roman army. Apollodorus's siege engines played a crucial role in overcoming these defenses, allowing the Romans to breach the walls and capture key strongholds. Historical accounts of the sieges of Sarmizegetusar and other Dacian fortresses suggest the use of advanced siege technology, including powerful ballistae and catapults capable of inflicting significant damage on enemy fortifications. While specific details regarding Apollodorus's direct involvement in these sieges are scarce, it is reasonable to assume that his expertise in military engineering contributed significantly to the Roman success. Apollodorus's innovations in siege technology built upon earlier Greek and Roman traditions, incorporating existing knowledge while introducing novel design elements and theoretical refinements. He drew inspiration from the work of Archimedes, whose ingenious inventions had played a crucial role in the defense of Syracuse. He also learned from Vitruvius, whose asterisk to architecture asterisk provided a comprehensive overview of Roman engineering principles. Apollodorus's unique contribution lay in his ability to synthesize these diverse influences, combining theoretical knowledge with practical experience to create highly effective siege engines. He emphasized the importance of mathematical precision and empirical testing, ensuring that his designs were both theoretically sound and practically viable. The innovations that distinguished Apollodorus's work include his emphasis on adaptability, his precise mathematical calculations, and his exploration of new materials and construction techniques. He recognized that siege warfare was a dynamic process, requiring a flexible approach that could adapt to changing circumstances. He stressed the importance of tailoring siege engines to the specific characteristics of the target city, taking into account its terrain, fortifications, and defensive capabilities. His precise mathematical calculations allowed him to optimize the performance of siege engines, maximizing their range, accuracy, and power. He experimented with new materials and construction techniques, seeking to improve the durability and efficiency of his designs. Apollodorus's contributions directly influenced later military engineers and the development of siege technology in subsequent centuries. His treatise Polyarchitecture, despite its fragmentary state, served as a valuable source of knowledge for Byzantine and medieval military engineers. Byzantine military treatises, such as the Asterisk Strategicon Asterisk of Maurus, reflect Apollodorus's emphasis on adaptability and mathematical precision. Medieval siege engineers continued to refine and improve upon the designs of ancient siege engines, incorporating new technologies such as trebuchets and gunpowder artillery. The principles of projectile trajectory calculation, lever system optimization, and torsion spring design, which Apollodorus had explored in Polyarchitecture, remained fundamental to the development of siege technology throughout the Middle Ages. For example, the design principles Apollodorus explored for optimizing the release mechanisms and torsion catapults find echoes in the later development of trebuchet release mechanisms, where precise timing and force application were crucial for maximizing projectile range and impact. Further research into the mathematical principles he outlined for calculating projectile trajectories can be seen in the later ballistic studies of figures like Niccolò Tartaglia, who developed new equations for projectile motion influenced by the earlier, though less sophisticated, approaches used by Roman engineers. Apollodorus of Damascus left behind a complex legacy, one inextricably interwoven with both architectural innovation and imperial intrigue. The accounts surrounding his demise, particularly those detailing a fraught relationship with Emperor Hadrian following Trajan's passing, warrant careful scrutiny. These narratives suggest a potential clash between Apollodorus's established authority and Hadrian's own architectural predilections, a conflict that may have culminated in dire consequences for the esteemed architect. One interpretation of these events posits a divergence in architectural sensibilities. Apollodorus, deeply rooted in the pragmatic Roman tradition, favored monumental structures designed to project imperial power and serve practical purposes. Hadrian, conversely, exhibited a pronounced inclination toward Hellenistic aesthetics, a style characterized by its emphasis on idealized forms and intricate ornamentation. This aesthetic chasm potentially fueled friction, with Hadrian perhaps perceiving Apollodorus's designs as overly functional and insufficiently refined. Another hypothesis centers on professional rivalry. Hadrian harbored architectural ambitions of his own, exemplified by his active involvement in the design and construction of the Pantheon. It is conceivable that Hadrian, Eager to assert his architectural prowess, viewed Apollodorus as a formidable obstacle, a figure whose towering reputation overshadowed his own aspirations. This perceived competition, tinged with imperial authority, may have engendered resentment and ultimately contributed to Apollodorus's downfall. The specific allegation that Apollodorus openly criticized Hadrian's design for the Temple of Venus and Roma serves as a focal point for these controversies. According to historical accounts, Apollodorus ridiculed Hadrian's design, deeming the temple's seated statues too large for their respective cells. While the veracity of this anecdote remains debated, it underscores the potential for conflict between the two figures, highlighting Apollodorus's perceived audacity in challenging the emperor's artistic judgment. The claim that Hadrian subsequently ordered Apollodorus's execution remains a subject of historical debate. While some ancient sources assert this to be the case, others remain silent on the matter. Determining the truth requires a careful evaluation of the available evidence, considering the biases and agendas of the various historical accounts. Regardless of the precise circumstances surrounding his death, the narrative of Apollodorus's conflict with Hadrian serves as a cautionary tale, illustrating the precarious position of even the most celebrated figures within the sphere of imperial power. Apollodorus's lasting influence on Roman architecture and engineering is undeniable. His innovative utilization of concrete, a material that revolutionized construction techniques, enabled the creation of vast, durable structures that continue to inspire awe centuries later. The markets of Trajan, with their intricate network of vaulted spaces and shops, stand as a testament to Apollodorus's mastery of concrete construction, showcasing his ability to create functional and aesthetically pleasing spaces on a grand scale. His profound understanding of structural mechanics allowed him to design buildings that were both structurally sound and visually impressive. Apollodorus's designs for Trajan's bridge, spanning the Danube River, exemplify this expertise. The bridge's innovative use of timber arches and concrete piers demonstrated a sophisticated understanding of load distribution and material properties, enabling the construction of a structure that was both strong and elegant. Apollodorus possessed a remarkable ability to seamlessly integrate aesthetics and functionality, creating buildings that were not only practical, but also visually compelling. The baths of Trajan, with their elaborate decorations and spacious bathing halls, exemplify the synthesis. Apollodorus's design created a luxurious and inviting space for public bathing, while also incorporating advanced engineering features such as hypocoursed heating systems and efficient water management. Apollodorus served as a crucial bridge between the practical demands of Roman imperial power and the theoretical principles of Greek engineering. His work embodied a synthesis of these two traditions, combining the Roman emphasis on pragmatism and efficiency with a Greek focus on mathematical precision and aesthetic harmony. This fusion enabled him to create structures that were both functional and visually stunning, reflecting the power and grandeur of the Roman Empire. His contributions to the development of large-scale public works were transformative. The Forum of Trajan, with its vast open spaces, towering columns, and elaborate sculptures, exemplifies Apollodorus's ability to create monumental spaces that served as both centers of civic life and symbols of imperial authority. The Forum's design incorporated innovative engineering features, such as an elevated marketplace and an underground drainage system, demonstrating Apollodorus's commitment to both aesthetics and functionality. His impact on military technology was similarly profound, as evidenced by Polykidiker. Apollodorus's expertise in siege engineering enabled the Roman army to overcome formidable fortifications and conquer new territories. His designs for siege engines, such as ballistae and catapults, incorporated advanced principles of mechanics and projectile trajectory calculation, giving the Roman army a significant advantage in siege warfare. The principles he articulated for optimizing the release mechanisms in torsion catapults, for example, directly influenced the later development of trebuchet release mechanisms, highlighting the enduring relevance of his work. Apollodorus of Damascus remains a pivotal figure in the history of architecture and engineering. His innovative designs, mastery of materials, and ability to integrate aesthetics and functionality left an indelible mark on the Roman Empire and beyond. His legacy serves as a testament to the power of engineering and architecture to shape societies and commemorate achievements, reminding us that the built environment is not merely a collection of structures, but rather a reflection of our values, aspirations, and collective identity. The enduring relevance of his work lies in his ability to demonstrate how engineering and architecture can serve as powerful tools for shaping our world and leaving a lasting legacy for future generations.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.